this computer. Cool. Well, hello everybody. Welcome to the PHYS1A revision session. My name is Rihanna, and today I'm just going to be going through some past paper exam questions, and we'll get started. So this hour is going to be the PHYS1A revision. And now I'll go find the share screen button. Okay, so for PHYS1A, I've selected a few questions from the term 1 2019 paper, I believe. That is available to you on your course page. I think like near the top, there's a tab that says past papers. So this is from when exams were in person. So they're probably going to be formatted a little bit differently to yours, but still kind of the same concepts. So I've kind of chosen two from mechanics and then one from thermal and another from the last topic, the wave one, and we'll just go through them. Feel free to put any questions you have in the chat, or turn on your microphone and ask me as I go along to explain something better or ask a general question. Anyway, I have here question 2B for that paper, which I said was the 2019 term 1 paper. And 2B is a rotational inertia one, which I guess is pretty notoriously interesting, let's say, in terms of learning that concept in PHYS1A. So we've got this question here, and the first part just says, give an equation that defines the rotational inertia of a continuous distribution of matter. State briefly the meaning of your terms. Now, this probably won't come up in your exam because that's a little bit difficult to ask in an online paper, but it's going to help us answer the next few questions if we just get started. So for part I, the equation that defines rotational inertia for a continuous system is I for moment of inertia is equal to the integral over the entire body of a system, r squared dm. And we'll just go through and look at all the terms. So this integral just means going to integrate over has a v in it, over full body of whatever we're considering. So a rod, a ring, a disc, or whatever. R is the distance from the axis of rotation, which is going to become a little bit clearer in the next part of the question, but you guys should know this by now. And then dm is an infinitesimal, I never know how to spell this word, infinitesimal, that's probably wrong, mass element. So we're essentially looking at whatever solid system this is with mass and volume, and we're integrating all the tiny little mass elements by the distance from the center of rotation squared. And that gives us this moment of inertia, which helps us to define any rotational motion later on. All right, so part 2. Now we do an actual question. So we've got a uniform thin rod with mass m. It lies on the x-axis from -a to b. And by considering small elements of length dx, derive an expression for the rotational inertia or moment of inertia of this rod about a perpendicular axis through x equals 0. So we're imagining some sort of magical imaginary axis, and this rod is spinning around it like this. we want to find the value I, the rotational inertia, that's going to define how this moves. And it's a little bit funky in that it's not an equal amount of mass on either side. We know from theory that I of a rod in general is equal to 1/3 ml squared, but they've asked us to consider the small element length dx. So we're going to derive it from scratch using this equation here. So let's just draw out our rod again. This is x equals to 0, x equals to -a, x equals to b. Now we need to find all these terms here. And the first one that's going to be a little bit tricky to figure out is dm. So dm is going to be the mass of the rod, but we were told in the question that it is uniform, which means every tiny little dx component, say this is dx, it's going to have the same mass for anywhere along the beam, which means we could define the relationship between this mass and the length by ratios, where dm, the mass of this tiny little amount over the full mass m, is going to be equal to the length dx over the full length, which in this case will be a plus b. So not too complicated of an equation. We know this is pretty typical uniform mass. These tiny little elements are going to be relative to their size, just because it is that uniform density. And so just putting that m on the other side, we now have an expression for dm in terms of dx, and we know how to integrate over a length, right? We've done that a billion times. So we take this equation here. We know r squared in this case is our distance of an infinite small element to the center of the rotation, or that rotational axis. So that's just going to be the value x, and we can pretty much solve it now. So I equal the integral of the body r squared dm. In this case is going to be the integral of x squared, because that's the only axis we're working in, m dx on a plus b, our equation for dm. And because we're now just looking at a line integral, this goes from -a to b. And now I can solve that. Take all the constants out the front, m on a plus b, solving this integral x squared dx, not too complicated, could do this in like year 11 or something. A plus b, that becomes x cubed over 3 in the same limits. And that gives us m a plus b 1/3 b squared plus a squared. And we can pretty much leave it like that. Sweet. Yeah, so that's all they really wanted us to solve, finding the moment of inertia for that kind of rod. Then part 3, a mass m is fixed to the end of a thin rod of mass of big M and length L, which turns freely about the other end of the horizontal axis at right angles to the rod. The rod is horizontal as shown, and it's going to be released swinging downwards and tracing this circular arc. And we want to find out what's going to happen for the speed m at the instance when the rod is vertical. State carefully any principle you may apply and briefly explain to the marker why this is applicable. And they've already given us a hint of one of the assumptions we're going to make. M is small enough to be considered as a particle. So let's just draw out our system. I would highly recommend drawing any systems just in your working out, because it helps to figure out what's actually happening. So we've got this rod, a little ball at the end of it. This is mass big M and this is mass little m. and it has a total length of L. This is going to swing downwards to this final position. Same length on this side. And we want to figure out what the velocity is going to be. So the assumptions we made was m is approximately a particle, which means we don't really have to consider that rotational inertia for it or any kind of like weird, I don't know, moving mass part things. It's just point mass moving through space. Another part in the question that gives us a hint about how to solve it is that air resistance is negligible, which means that we don't have any non-conservative forces. And this should be pretty much drilled into you, but if there's like if there's no non-conservative forces, then they don't do any work. And basically we can apply the magic of conservation of energy. So we're going to use conservation of energy to solve this one. And I think that's the clearest method of solving this, just because we have been given this direct path to solving the problem, looking at rotational inertia and then all those hints about neglecting air resistance. It's all those little things about how they phrase the question that indicate which method you're going to be using. So in this case, we have all the details which can help us find the kinetic energy, because we have the mass and we're looking for a velocity. We just went through how to find rotational inertia, so we know how to find the rotational parts of kinetic energy. And gravity is always going to be there, so we can slip that in as well. In this case, conservation of energy, it's going to be the potential energy of the initial state plus the kinetic energy of the initial state is equal to the potential energy of the final state plus the kinetic energy of the final state. And what is this? Initially, let's go back up to our question. It says it is released, blah, blah, blah. Doesn't specifically say that it is released from rest, but we don't have any way to define that initial one. So I think when it says that the rod is horizontal and then it's released, we're assuming that it's released from rest. That's usually the implication of it's being held and then it swings down. So that gets rid of our kinetic energy, and our gravitational potential energy, we can just set some kind of arbitrary reference and then solve it from there. So let's set this as our reference for grav equal to 0. Or the height is equal to 0, let's say that. That's more physically accurate. H is equal to 0, that's the wrong color. So our initial potential energy from gravity, we know that's mgl, because at the top, it's of course the full length of that rod above this boundary of where we're going to set our gravitational potential energy to equal to 0. So at the beginning, both the mass of the rod and the small mass of the particle at the end are that full L length above. So the little mass plus the big mass, that's our initial potential energy, and we said our initial kinetic energy was assumed to be 0. Now, well, let's add that to our list of assumptions. Released from rest. And then what is our final gravitational potential energy? Let's see, I went too far. At our final position, our particle is at this reference that we set. for gravity potential energy to be equal to 0. So there's no potential energy for that small mass now. And we're going to consider just the mass of the rod. In this case, our gravitational potential energy, that distance value, we measure that from the gravitational center of a rod. So in this case, it's going to be the center of this uniform rod. And now above this datum line, this is going to be L on 2. And so that's our parameter that we put into our potential energy equation of just mgh. So in this case, mg L on 2. And because it's lost all this kinetic energy, the potential energy that it started off with, and now only has a small amount, that's going to gain a lot of kinetic energy. And we want to figure out what form that's in. And we're pretty much going to split it into the rod and ball components again. Now for the ball, we're assuming it's a particle, right? So because it's got no physical body, there's no real definition for rotational motion. And we can pretty much define this exclusively just by linear kinetic energy. Or linear velocity. It just moves in this v way and doesn't really care about what's rotating about it. The rod, on the other hand, the rod is fixed. It's fixed about this point at the end and it's going to rotate about it, which means we can define all the motion just in terms of rotational kinetic energy. Okay. We could define certain points along it as having linear velocities, but if we're considering the whole rod, it is much better defined just by linear rotational kinetic energy. And if that doesn't make any sense to you, I'm going to write out the forms of what those are, and then maybe you'll be like, oh yeah, I remember that. So for the ball, that's just going to be half mv squared. That's exactly the kinetic energy that this ball moving through space has, can be completely defined by that. The rod, on the other hand, we can easily find that rotational inertia value, and so we can define the kinetic energy of this purely rotating body. It's not also being thrown, it's just rotating about a fixed point, as half I omega squared, where omega is that rotational velocity. And these two values are related by omega is equal to V on L. So we've got some sort of rod, the end has a velocity like this and a length L, and we can define the angular rotation by the velocity over the length. And so now we've got this big equation that defines it all. We know the mass terms, we know the length terms, gravity. We don't have the actual values of it, so we're going to leave our results just in terms of these parameters. And we can rewrite the angular velocity in terms of the linear velocity. And then we can also rewrite this moment of inertia in terms of m and l as well. And we'll just use the known value for a rod fixed at the end rather than deriving it again. We've already done it, so we can just use I'll go back to the black pen. I for the rod is equal to 1/3 ml squared. And we'll rewrite this whole equation. I'll put all the gravitational potential energy values to one side. So that's going to be m plus big M on 2 GL. So that's these two values combined together, subtracting this value. And then on this side, we'll have the kinetic energy terms. In this case, it is half mv squared plus half the moment of inertia of the rod and the angular velocity squared. rearrange that all to get it into some term that gives us what the velocity is going to be. And I won't go through that because it's going to be tedious, but V ends up equaling this big square root GL 2m plus m over m plus m on 3. Nice. So that's it. That's question 2B. I think the tricky part is just knowing how to start this last question. So it's just seeing all those, sneaky hints in the question, like, we've got mass and we're finding a velocity and air resistance is negligible. So using that, your mind might go to conservation of energy. I guess the difficult part for the second question could just be, I don't know, not being sure about your solution, or maybe you dropped a term, in which case you know how to get this equation for moment of inertia of a rod that's in a formula sheet, or even if you forget, you can Google it. It's an online exam. Google the general forms of rotational inertia, and then you can sanity check your derived question. All right. This is T1 2019, the 1131 paper. All right, let's do question 3. So this is another mechanics one, but it's looking at like gravity and other fun stuff like that. I skipped the question 1 for this paper, which is just like particle kinematics. I felt like that was pretty simple, but you can absolutely go back and do the rest of this paper. I just chose the questions that I thought were a little bit tricky. All right, so question 3. Consider many tiny particles coming together from rest at a very large separation, approaching by gravitational attraction, then undergoing complete inelastic collisions to form a uniform sphere with mass m and radius r. This is a very, very oversimplified model for the formation of a star. And first, state in just a few words why the resultant sphere must be at rest. So in this case, we're assuming we're looking at the full expanse of the universe, and there are all these particles coming from the outer regions of space. And they're all being attracted towards each other, and the resultant vectors kind of look like this. They're all coming together. Now, the final mass that it forms, so this star in the center, must be at rest due to conservation of momentum. And that's essentially because we've got, like, say we just have a 2-particle system and they come together. If they have perfectly equal velocities or perfectly equal momentum and they hit each other purely inelastically, then their momentums, because they're coming in opposite directions, are just going to cancel each other out. And so for this system, we've got so many tiny particles coming from every distance to one spot. And so it is highly likely that there's going to be an equal and opposite particle. And once it all comes together, it's just going to cancel out and be at rest. So that's part I, basically just the magic of conservation of momentum. Cool, part 2. Consider a uniform sphere of radius r coated with a thin layer of thickness dr, give an equation relating the mass and radius to, and another relating the infinitely tiny small mass and radius components. Using the density of the material, assume uniform in this simple version. Hint, use surface area of a sphere for the second part. All right, so let's try and draw whatever the hell those words were trying to mean. There were a lot of words in that. So we've got some sort of sphere, and like the rod equation question where we were considering just a tiny amount of the rod going along, we're going to consider a sphere with tiny little shell layers. So like an onion, really, they're just tiny little layers. So this is dr, this is r, and this is dm, and the whole thing is m. And basically we're looking at density, right? And we know density is rho and it's mass over volume. So it's just a ratio. And so with that respect, we could say that rho is also equal to the mass of the tiny shell over the volume of the tiny shell. We got to figure out what that volume is going to be. And imagine we just like unwrap this. This length here is going to be 4 pi r squared. Actually, it's going to be like a square. No, it's going to be a circle. It's the surface area of a sphere, right? dV is going to be 4 pi r squared times dr. So it's like surface area of sphere times the thickness of this blanket layer covering it. And so we can then write out our little mass. dm is equal to rho, our density, times 4 pi r squared dr. And we can also write this using the same method for a full sphere, in which case m is just going to be rho 4 on 3 pi r cubed. So this is for a full sphere where we've got the density times the volume of the sphere and the full mass. So that was a question that's kind of setting up how to solve the next part. So part 3, think of the gravitational potential energy of M1 and M2 at separation R with respect to a very large separation. The result may be applied when M1 is a uniform sphere and M2 is that small thin coating around the outside. And we're going to use these results to derive an expression for the total loss of potential energy in the process of turning many tiny particles into this star in the center. And they've given us a hint about the form of what our answer is going to look like. So that's nice. All right, part 3. So we're basically looking at what's going to happen when we bring all these particles to the center and they're going to form this star by coating the sphere in layers of dr. All right, so we know our gravitational potential energy equation is like U is equal to negative G M1 M2 over R. And so we can find out what this is going to be in terms of mass 1 is our original sphere and mass 2 is our thin layer around the outside. And we'll call this du because we're going to have this term dm from that little thin coating around the outside. So that's negative G, M1 is just mass of the sphere M, and M2 is dm over R, the radius of the sphere. And so because the potential energy was initially 0, as stated in the original question, the initial and final kinetic energies must also be 0 because it started from rest and it came together, and we said because of conservation of momentum, it's going to end at rest. So the change in the mechanical energy must be equal to this potential energy that I've just written, which is a lot of words, but it basically means that initial and final kinetic energy, run a space, energy is 0. because the systems are at rest. Our initial gravitational potential is 0. And so change in energy of this formation is equal to that gravitational potential energy of this now final system. And so we write this as dE is equal to -g m dm over r. And when this is the energy of how we like form our sphere, I suppose, by those layers of when particles keep coming and getting stuck together. And so we form this sphere by radius growing from r equals 0 to r is equal to the big R total final radius of the sphere once it's completely formed. And so let's just remind ourselves of what we're actually finding. Part 3, what do we want? We want to derive an expression for the total loss of potential energy for the process of turning many particles into this big star. So to find the total energy, we're going to have to integrate this over this process of when it goes from its initial state to its final state. So that's just going to be E is equal to R equal to 0 to big R -g m dm over r. Now we've got an integral going from a distance to another distance in terms of our mass. So that doesn't really make sense. We're going to have to bring in what we did in the first question to get this into a form that we can actually solve mathematically. So this is going to now equal to 0 to r -g, and we'll just sub in our equations for mass and little mass, which is rho 4 on 3 pi r cubed times rho 4 pi r squared dr. Now I've got this dr term, we can solve the integral, and this is all over r. And we'll take the constants out the front so we can see what kind of integral we're actually working with. And so that's -g 4 on 3 pi. We can put some squares there because there's quite a few of those. And it's 0 to r to the 4 dr. And we just go through and solve that. -g, let's change that to a 16 on 3 pi squared rho squared of r to the 5 on 5 minus 0. Just subbed in those values again. Pretty simple integral of a polynomial. And that gets us -g 16 on 15 pi squared rho squared r to the 5. And this is our total energy that's happened in the system. And going back to the question, it gave us a hint that it was going to be in the form n gm squared on r. So we basically need to find n. So the hint said E is equal to n gm squared on r, which is not quite the form we have. So we're going to have to get this density value and put it back into terms of mass. So this turns out to be E is equal to, might actually be easier to go the other way and swap in m for a value of density. So let's go between these equations. That's going to be n g on r 4 on 3 pi r cubed rho squared. So this is our mass of the final sphere. And then now we just compare this with this one. And what we get is n is equal to 16 on 15. And we've got another term of 4 on 3 squared for this equation. And that results in n is equal to 3 on 5. So using the form that they gave us in that question, E is then 3 on 5 g m squared on r. Boils down to a nice little expression, doesn't it? All right, part 4. Our sun doesn't have a uniform density, of course, but let's use this as a very rough approximation for a crude estimate. And they've given you a value of n you can use just in case you were running out of time and you're like, I can't figure out this question. So you just put in a dummy value and you'll get it correct from previous answer. So they've given us the values of the sun, and we want to calculate the order of magnitude estimate of how long our sun could shine for at this rate, assuming that this is the power. All right, this is a very simple approximation, so we're going to expect it to go wrong, but we'll give it a shot. So this is part IV. We know from somewhere in our notes, energy is equal to power times time, which means time is going to be the negative of that energy loss over the power of this sun shining. And if we put it in this energy value, we're going to have 3 on 5 g m squared r times p, power of the sun, and we'll just put in the values that they've given us. 3 on 5 g is 6.67 times 10 to the negative 11. Mass is 2 times 10 to the 30 kilograms, and this needs to be squared. The radius of the sun is 7 times 10 to the 8 meters, and no, I won't put units in there. And finally, the power was 3 times 10 to the 7. I believe all those values were given in the question. I just kind of started looking at my notes. Yes, they were given in the question, but if not, you can always Google them. It's an online exam. Gonna miss this next year, hey. And so that gives us time is equal to approximately 20 million years. And the last part of that question, in no more than 1 or 2 sentences, comment on your answer. All right, 20 million years is how long the sun is going to shine for, and then that's it, we're done. However, we have found out through science that the age of the sun is approximately 5 times 10 to the 9 years. So that's 5,000 million years. So why are we not dead yet? And that's because this approximation assumed that all our energy is just from classical mechanics. But alas, the world is more complicated than that. So this approximation neglected energy from nuclear fusion in the sun. And that's why we can't do all of physics with just classical mechanics, unfortunately. Honestly, I am not in contact with any kind of like admin relating to this course. I don't know if there are other rules, but it will absolutely say on Moodle. But yeah, typically with online exams, unless they've got like, you know, a strict, we're going to watch you through the camera kind of thing you should have set up already, then it's pretty much unspoken open book. But do confirm that with the course details. And somehow it is already 3:45, and I've only gone through half the questions, but that's okay. Mechanics is like half the course, so not all is lost. The next question. I have chosen a thermodynamic cycle question for the thermophysics part of this course. I like a good thermal cycle question. And I think it's a pretty easy one to ask in a Moodle form, because you've got to find out all these values at each point. So it's a good one to like put in like individual answers on a Moodle form. So that's my reasoning for why I've chosen this, but we'll go through it. So we've got 5 moles of an ideal diatomic gas. It undergoes this cyclic process, and they've told us what's happening at each of the processes. So from A to B, we've got an isobaric process, and 27.5 kilojoules of heat is added. From B to C, it's isothermal. From C to D, isobaric, and 34.2 kilojoules of heat is removed. And from D to A, it is adiabatic. All right, so let's answer. Part I, at A, how many degrees of freedom does each molecule of gas have? Provide reasons for your choice. Okay. So to figure out what the number of degrees of freedom is going to be, we need to figure out what the temperature of the gas is at state A. And that's going to determine if we need to figure out some like other things, or if we can just like guess. But we'll go through the maths of that first and then see what we have to work with. And because we are told it's an ideal gas, we can just use our ideal gas formula. So that's P, that's not a P. PV is equal to nRT. And that's going to be to find T. So at A, T is equal to PV on nR. This is, what do we actually have? We have 5 liters as our volume, and 16.48 atmospheres as our pressure, and 5 moles of the diatomic gas. Alrighty. And we can find R is 8.314 joules per Kelvin per mole. And so I guess the tricky part with this one is not getting stumped by these weird units. So we've got atmospheres and liters. So we'll put it in the form that we have. So it's 16.46 atmospheres times 5.00 liters. And that's divided by 5 moles. And there is a form of this R value in terms of liters, atmospheres per Kelvin per mole. And that is 0.08206 in atmospheres per Kelvin per mole. And that is 200.6 Kelvin. Alternatively, you can convert everything into SI units, or you can Google it, find the form of that R value in terms of the weird units. But yeah, those are the numbers. Personally, I like to convert everything into SI units, and because it is an online exam, you just be like, what is liters to meters cubed, etc. Anyway, so that is T at point A, and then we can do the same thing for T at point B. Do we need to? Nah, just at point A. So that's the temperature at point A, 200 Kelvin, not particularly hot, so we can assume no vibration. Degrees of freedom, which just means we have 3 Cartesian and 2 rotational degrees of freedom. And that's just because we have a diatomic molecule, so it can move up to the side, up and down, side to side, or front and back, otherwise known as X, Y, Z. It can also rotate in this way. No, that will look the same. It can rotate this way and, oh yeah, no, it must be that way. Can rotate in 2 degrees of freedom. And that's pretty general rule for a diatomic gas. If you did have a temperature that was like, I don't actually know what the threshold is, but if you had a very, very, very high temperature, then there might also be vibration degrees of freedom, and you would then have to do more maths. But typically, they will hopefully only ask for the simple one where you just prove that it's at a reasonably low temperature and you just go bang, 3 Cartesian, 2 rotational, therefore 5 degrees of freedom. Is the pressure 5? Oh yeah, you're so right. Sorry, the other way around. Alrighty, part 2. So that was a very long way of double checking that we have 5 degrees of freedom. But part 2 is what is the work done on the gas as it goes from A to B. All right, we're finding the work. Our equation for work is work W is equal to negative integral of P dV. Now we've got an isobaric process, which means that our pressure is constant, as we can see on the graph, and integral of a constant value is just negative P times the change in volume. Too easy. So we'll just put in the values for that. -5 atmospheres, and we can convert that into pascals, which is timesing it by 1.01 times 10 to the 5, which is atmospheric pressure in pascals. And then our change in volume, our final volume is 32 liters minus 16.46 liters is 32 minus 16.46, and we'll times it by 1 times 10 to the -3 to get it into meters cubed. And that gives us -7848 joules. Excellent. In the question here, they've actually said -7850 joules in 3 sig figs, because the values we were given in the question were in 3 significant figures. And then part 3, what is the change in internal energy as the gas goes from B to C? Okay, internal energy. Internal energy is delta E int, and it is equal to Q plus W. So we'll keep that in mind. And then work done from, change in internal energy from B to C. And it's actually an isothermal process. What do we know about isothermal process? Change in temperature is equal to 0. And we know that the internal energy can also be calculated by F on 2Rn change in T. So this was for nothing. Our internal energy is just equal to 0 for that one. Too easy. And last question for this part is what is the change in internal energy as the gas goes from D to A? So D to A is our adiabatic process. Now we can use that internal energy equation. Internal energy is equal to Q plus W. We've got an adiabatic process, which means that Q is equal to 0. So now we can solve this by either finding what the change in internal energy is using this equation here, or we can calculate the work using this equation here. Personally, because we can use this temperature equation from the ideal gas law, it's probably going to be easier than finding out what that integral is. And so we're going to do that one. So we're going to say change in internal energy equal to F on 2 Rn TA minus TD, so final minus initial. TA we found before, TD is going to be, what are our values? 2 atmospheres and 31.67 liters. 2 atmospheres times 31.67 liters over 5 moles times that 0.08206. So when you're in atmospheres, liters, kelvins, and moles, and that is equal to 154.4 Kelvin. And so we'll just stick that into our equation. Change in internal energy. We found out before that our degrees of freedom were 5, and this temperature is even lower than the previous one, so it's definitely still no vibration. That's just F is 5 on 2, our degrees of freedom over 2. This time, we'll just put it in SI units. So our R value is 8.314. Our number of moles is 5, and our temperature is 200.6 Kelvin minus 154.4 Kelvin. And that gives us 4801 joules. Alternatively, you could have found the change in energies for the entire cycle, and we know that for the full cycle, our energy is going to be 0. And so you can find all the components just because they have given you when heat was added at that A to B and C to D process. But I think this process was just as easy. And we have 4 minutes to do this last question I had in mind. Maybe we'll just do one of them. So this is the last topic with waves, and essentially it's all just maths. That's all you really got to consider. It's just going to be, how does this wave move and how can we rearrange what form we're given into the details we want to know, etc. So let's do part B. So we've got a transverse wave at x is equal to L, and it undergoes simple harmonic motion described by this value here. So say we've got this string, this is x equal to 0, and this is some point x equal to L. And at x equal to L, this goes up and down in this kind of motion with respect to time. So we want to write down an expression to describe the height of the string along its length. So in terms of x. And to figure that out, let's just write out the general wave equation. So that's just going to be y is equal to a cos long kx, so our wave number k, plus omega t, where omega is our just like speed kind of thing, plus phi, our phase of the wave. And then we'll just go through and figure out what those values are going to be. So A is just going to be the same amplitude as just the time equation of the wave as it goes at this point here. We assume that that's just as far as it goes. So A stays the same. A is equal to 0.05. What else can we find? We can find the like omega, the angular frequency of the wave, because we have found out that the wave speed is 1.00 meters per second to the left. All right. Oh yes, another point is that normally this is a negative, but because of this to the left, it means that we have the plus omega t term. So that's why that's there, in case you're like, I don't recognize that form. It's because of that to the left thing. And what else do we have? We've already got omega value actually, and it's 2.00 t. So we'll put that in. Omega is 2.00. That's radians per second. That's in meters. And so now we just got to find out what that k value is. K, our wave number. K is given by a typical formula. That's 2 pi on lambda, the wavelength. Alternatively, we can figure out what that's going to be in terms of these angular frequencies and the speed of the wave. So let's say we said 2 pi f on lambda f, so we just times it by f on f. Doesn't really change anything, but now 2 pi f is our angular velocity, angular frequency rather, and our wavelength times our frequency just becomes the speed of our wave. And so we know those. Our angular frequency was 2.00 and the speed of our wave was 1.00 meters per second. So our k value is just 2. And that's in radians per meters. And so now we just need to find our phase value. And we can find that by looking at our initial conditions. So we can assume these values here at t equals 0, y is equal to 0.05 meters, and x is equal to 0. So let's stick that in. So initial conditions, 0.05 is equal to 0.05, our amplitude, cos. So when time was equal to 0 and space was equal to 0, and we just got to find out what our phi value is going to be. So the only way these are equal is when cos of this, cos phi is equal to 1. And that occurs when phi is equal to 0. So we can just write this now as y is equal to 0.05 meters cos 2.0 x plus 2.00 t. And it is 4 o'clock. So that is all I have time for the PHYS1A part. If you have any other questions, please feel free to ask them. Yes, I will start the revision lecture for 1B in a minute. No worries. If there was anything that you were still unsure about, there's still that Women in Engineering run revision session on Wednesday. So show up to that. I am also running that. So I'm just going to do the rest of the questions. No worries. Good luck for your exams. Okay.